So that you will have a better understanding of what Rockide coatings are and some of their useful features which may be of help to you, the following scenes show the Rockide equipment in operation and some of the commercial and the military applications of these versatile coatings. In general, hard, adherent, and flexible refractory oxide coatings can be applied directly to the surface of metal with metallizing type guns utilizing solid oxide rods called Rockide rods. Here you see the production coating of a large thrust chamber with a 4-gun arrangement to apply the coatings at minimum cost. The protective Rockide coatings are providing insulation from the high heat and erosive forces of combustion with minimum increase in weight. The 4 guns are seen from the operator end with the gun support arms attached to the traversing mechanism of a lathe. The Rockide Z is being applied approximately 90 thousandths of an inch thick at the throat and being feathered out to 10 thousandths of an inch thickness at the exit end. Let us look at the Rockide rods and Rockide guns in closer detail. There are 5 commercially available Rockide rod compositions manufactured in 1/8 inch, 3/16 inch, and 1/4 inch diameters. Aluminum oxide rods are designated Rockide A, zirconium oxide as Rockide Z, and the zirconium silicate as Rockide ZS. 2 recently available compositions are magnesium Rockide MA and chrome oxide designated Rockide C. To melt these ceramic rods, atomize and project the molten particles onto the base material, metallizing type of guns have been adapted. The R2 turbojet gun, developed by the Metallizing Company of America for 1/4 inch rods, has a fine magnetic control device of the rod feed rate, which maintains close control of the coating quality. The guns can be obtained with extensions to permit coating of internal diameters as long as 16 feet. Three sizes of this turbojet are operating simultaneously. Reading from the bottom, the 1/8 inch R1, the 3/16 R1, and the new 1/4 inch R2. Areas that can be coated with 1/24 inch Rockide A rod of each size are shown by the size of the white plates. For a 10 thousandths thickness, the 1/8 rod coats 20 square inches, the 3/16 inch rod 36 square inches, and the 1/4 inch rod 70 square inches. Materials and labor costs are substantially reduced with a 1/4 inch gun. Prior to coating, the part surface may require some preparation. Utilizing standard pressure blast cabinets and aluminum oxide abrasive, you can observe the uniformly roughened surface on a small metal plate being blasted. The metal is upset into a Christmas tree pattern, which permits the finely atomized ceramic particles to embed and interlock with the metal and ensures a firm bond. Cleanliness at this point is mandatory to assure good coating adherence. Masking of areas not to be coated may be required prior to pressure blasting. A mechanical seal is being masked on the OD with bare manning masking tape prior to sandblasting of the end surfaces to be coated. Rubber plugs provide an economical production method of masking ID surfaces to be protected. Steel shields of suitable shape are also used to mask the part when production quantities warrant a special shield design. To increase the adherence of Rockide coatings still further, metallized undercoatings may be required. Nickel chrome is most frequently used as an interlayer between the metal and ceramic. This sandwich compensates for the differences in the expansion rates of metal and ceramic and contributes resistance to thermal shock and chemical attack. Moly and other coatings are occasionally used for special coatings on graphite and other materials. Here a large paper mill roll is being metallized with 6 thousandths to 8 thousandths thickness of nickel chrome to ensure excellent adherence of the coatings and improves the corrosion resistance of the completed part. Metallizing can be accomplished by hand if necessary. As in the case of this large mold part, too heavy to be rotated mechanically. Rockide coatings can be similarly applied. One of the predominant features of Rockide is its flexibility. Thin coatings alone can flex like paper. By flexing with the base material, Rockide withstands substantial vibration and distortion without loss of adhesion. Here the coatings are being abused to demonstrate their ability to conform to the distortion of the base metal when subjected to the action of a ball-peen hammer. Although it is somewhat difficult to see, all that has occurred is a slight powdering of the coating at the surface where it conforms to the indentation of the hammer. In addition to providing heat insulation at high temperature, the coatings are capable of withstanding substantial thermal shock without failure. To demonstrate this, a sample of Rockide A is shown being heated to over 1900 degrees F in an electric furnace and then plunged directly into a cold water bath without loss of adherence of the ceramic coatings. This is not recommended procedure with any ceramic, but demonstrates that despite the warpage of the steel plate and tremendous heat shock, the coatings remained firmly bonded to the metal. To illustrate the excellent insulating characteristic of the Rockide coatings, we first show you a metal plate being exposed to an oxyacetylene flame for approximately 6 seconds. The 1/8 inch thick steel plate is burned through, while after 10 seconds of similar exposure, the Rockide coated plate with 25 thousandths of an inch thickness of Rockide A has provided the base metal with an effective heat barrier from the over 5,000 degree flame under these non-equilibrium conditions. The plates side by side show the slight fusing of the aluminar coating, but when the plates are reversed, there is little or no discoloration of the ceramic protected plate. For electrical insulation, Rockide A has been used predominantly. A 10,000 volt arc jumps easily to steel, poorly to Rockide A, and does not arc to an epoxy impregnated Rockide A plate. Resistance of more than 100 volts per mil thickness may be expected from Rockide A alone. Applications to industry are increasing rapidly and cover a wide variety of sizes, shapes, and physical properties. Here you see a fine wire coil utilizing Rockide A for electrical insulation, further demonstrating the flexibility and adherence of the coatings. A similar fine wire application for electrical insulation is the embedding of strain gauge grids on the surface of metal, while protecting the grid from high temperature. This suggests that other electrical components may be mounted successfully to various materials or fabricated from the coatings themselves, as in printed circuits. Application of Rockide C to the multiple face of a meionite capstan wheel, drawing low carbon steel wire at 1250 feet per minute, improves the wear life of these capstans at least 3 to 4-fold while reducing equipment downtime. To help the paper industries develop a press roll of superior wear life and to reduce so-called fiber pickup, Rockide A is shown being applied to the steel with a 3-gun arrangement. Following the coating of 50 thousandths of an inch thickness, it is ground with a silicon carbide grinding wheel to 35 thousandths of an inch thickness, and results to date show excellent promise. To achieve close decimal tolerances and excellent surface finishes, grinding and lapping of the coatings may be required. An impregnated Rockide ZS bearing surface of a rotor used in a paper making machine is being carefully ground. This results in a hard, smooth, corrosion-resistant surface and was developed to extend its life when used wet against a Teflon sleeve. Grinding on these long printing rolls is accomplished with silicon carbide grinding wheels, resulting in an excellent 30 to 50 RMS finish on Rockide ZS. Previous wear life with hardened steel was 1 week, but with Rockide, 1 year. Mechanical seals ground and lapped developed flatness readings of 3 or 4 light bands. A profilometer shows the surface finishes obtained by grinding and lapping of the various coatings. A, Z, and ZS show a range of 30 to 50 RMS, while Rockide C, chrome oxide, results in 7 to 10 RMS. A wide variety of non-metallic materials can be successfully coated, such as fiberglass plastic sheet, Havig phenolic plastic, silicon carbide, graphite, wood with a copper undercoat, fiberglass on graphite, aluminar ceramic brick, recrystallized silicon carbide, and quartz. These are only a few of the increasing number of materials being tested for use with Rockide. To coat unusual new materials, variations of coating, technique of coating application, and temperature of the process can be made to ensure good adhesion. Rockide has been particularly useful for protecting of missile nozzles and ramjet chambers for the military. 2 static tests of a 7-foot by 29-inch diameter ramjet engine produced by the Marquardt Aircraft Corporation are shown. Here it is fired with liquid fuel without the protection of Rockide on the ID surfaces. The metal is unable to withstand the 2200 degree F temperature and erosive forces of the high-velocity gases, and premature failure occurs at 14.2 seconds. In the second test, you will note the substantial flexing of the engine at the left-hand end as the combustion starts. In the right half of the ramjet has been coated in the light blue area, while the left-hand end, showing dark blue, is uncoated. Although the heat penetrates the bare metal, the coated area is effectively insulated and successfully withstands the vibration and erosive forces of the gases. Today, ramjets such as the Talos are protected with Rockide Z and nickel chrome undercoatings, and substantial increases in flight time are possible. This Swiss rocket nozzle of unusual shape on the ID was successfully coated and protected with 25 thousandths of an inch of Rockide A, and a temperature drop of 400 to 500 degrees F was obtained under non-equilibrium conditions. Nozzles of tubular construction are frequently used for larger liquid rocket nozzles and can be successfully protected with combinations of metallized undercoatings in Rockide Z. Here a missile nose cone is being constructed utilizing an automated gun arrangement to produce a thick-walled shape which after further sintering will have properties similar to a solid aluminar body without the problems of substantial shrinkage in firing. This method suggests fabrication of parts too large to mold or press with conventional equipment. Substantial numbers of missiles are now in the production stage and are in need of commercially available insulating materials of light weight and good erosion resistance to give uniform firing conditions and accurate flight. Solid fuel engines such as these are in production at Aerojet General Corporation. These include the Hawk, and the Sparrow, and the Bullpup, and the Tartar, and here shown the Polaris, and the succeeding Minuteman scene. All are being assisted in by the use of Rockide on nozzles. A view of the static test of the Polaris engines shows solid fuel gases at over 5,000 degree F. The erosive forces and corrosive action of these fuels is increasing as temperatures in the 7,000 degree range are considered and tested. Rockide is helping these successful flights of the air-to-air Navy Sparrow, traveling at over Mach 2, and the surface-to-air Army Hawk of similar speed. Here you see the highly regarded underwater-to-air Polaris for use with the submarine service. Liquid-fueled engines of many other vehicles, such as the Talos ramjet and the X-15 manned rocket, are also protected by Rockide. Your particular problems in design or use receives the active support of Norton's development facilities. Special impregnants of epoxy and silicone resins to close the pores of such parts as this roll to be used in the paper industry open the door to new areas where Rockide can be of help. Problems that cannot be readily solved are brought daily to our research facilities. Although we are unable to duplicate all conditions found in the field, many special tests are conducted to offer better information to our customers and representatives. This jet test rig permitted evaluation of various coating systems to obtain conductivity values of specific coating specifications. Using temperatures of 2200 degrees F at near Mach 1 velocity, various experimental coatings provided insulation resulting in temperature drops of 400 to 900 degrees F under 30-minute equilibrium conditions. Here let us summarize the major features of the Rockide coatings. They are flexible, adherent, and hard. They have very high melting temperatures, up to 4600 F, and they are generally inert to all chemicals. Demonstration and use have shown them to be excellent against thermal shock and capable of withstanding severe vibration and impact. The coatings provide excellent thermal and electrical insulation. They are applicable to many types of materials of unusual shape, and coatings can vary from a few mils to 1/4 and 1/2 inch thicknesses. They can be ground to excellent surface finishes in close dimension. Research continues on Rockide coatings to ensure that new coatings will be there to meet the new demands of industry. Work continues on superior impregnants to seal the coatings permanently against all chemical attack. New rod compositions and coatings to meet demands for specific properties are in development. To meet higher temperatures and velocities more effectively, combination metal and ceramic coatings are showing excellent promise. The use of plasma heat sources for rod flame spraying at lower cost are also under study. This is far from the end of the Rockide story, which is growing rapidly in its service throughout the country.